Hi everyone, welcome to our first GoFly Master Lecture in the year 2019. Welcome once again. It's my pleasure to introduce Gwen Leiter, CEO and founder of GoFly.
Hello everyone, and thank you for joining us, and happy and healthy new year to all of our GoFly teams and our sponsors and our supporters. As you know, GoFly's grand sponsor is Boeing. In addition to Boeing, we are joined by corporate sponsor Pratt & Whitney, as well as several of our in-kind sponsors who provide free and discounted software services and products directly to our teams. And in addition to them, we are supported by over 20 different international aerospace and STEM organizations. Today, I am so pleased to be able to welcome Ashish Bagai to give today's master lecture. So you all know, Ashish is the founder and the principal of buGiAero, committed to supporting the advancement of new and innovative concepts in wing, rotorcraft, and distributed propulsion air vehicles. He holds degrees in Aerospace Engineering from the University of Maryland in College Park. Ashish has worked in academia, industry, and the DoD. In academia, he has mentored design, build, fly teams to design, build, test, and demonstrate novel technological concepts such as a scaled electric advancing blade concept incorporating variable CG as a means of control, an amorphous reconfigurable flexible flying surface incorporating structural deformation for control and impregnated structural damping, and surface effect aircraft design. At the DoD, he developed and managed a strong portfolio in vertical flight concepts, both for mission applications and as technology demonstrations. He was also instrumental in the streamlining and execution of flight test planning, authorization and execution, and developing best practices. And in industry, Ashish has worked on a number of aircraft systems, most notably on the design of rotor systems and blade design. They're currently flying on a number of aircraft, including the S-76D, the CH-53K, and his most notable contributions were to the development of the X-2 high-speed helicopter. In his current role, he provides technical advisory, collaborative, and mentoring services in support of the development and testing of aircraft systems and designs, and has worked with large and mid-sized corporations, educational institutions, small startups, and government. And Ashish has a wealth of information for our GoFly team. So today I am so very pleased to welcome Ashish Bagai to join us as today's master lecturer.
Thank you, Gwen, Nidhi, Dan, for hosting online. The title of my presentation today is Executing for a Successful GoFly Journey. I'm going to offer some comments on this opportunity that is now well on its way and in its second phase of execution. In addition to any new teams that may have joined in at this time, it should be clear that you've been selected to proceed through this phase because you had the most creative and practical concepts that address the terms of the competition. But one might pause for a moment to ask what this competition really seeks to enable. It is about the win. Is it about the win incentive, or is it about the journey to do something that is remarkable and to along the way discover opportunities that would have otherwise been missed or overlooked? In my observance, GoFly is the type of opportunity that comes about in vertical flight related aviation only infrequently, perhaps very infrequently. And as you enter this phase two, where the expectation is to showcase demonstrable functionality of your aircraft, I thought I'd share some thoughts based on my experiences that might help you along your way as you mature your systems and your operational concepts. Given that this is a particularly crucial phase and moving on a particularly tight schedule, executing rapidly but with forethought and awareness will help your progress. So I offer my comments as guidance, and I hope that you are able to adapt what's relevant to your unique system and operational concept to facilitate your success. But first, let's pause and take a quick look at the design space that's available to us. While I understand that you have established your configurations and technical approaches, it is important to keep the larger design space in perspective. Traditionally, rotary wing and powered lift concepts have dominated the vertical flight configuration domains. These have been largely driven by the tightly integrated designs that have been driven by power and propulsion considerations, main rotors with low disk loading, gas turbine engines, mechanical transmissions, and gearboxes, multiple rotors, tail rotors, etc. And also compounding, of course, using auxiliary propulsion or lift offset, the addition of wings, if you will. However, these are no longer the technologies that constrain the design space, and distributed, aggregate, dissimilar, asymmetric configurations are now also possible with increasing likelihood of success, especially as those that are enabled at a practical level by electric drivetrains. Mind you, the GoFly competition is agnostic to configuration and technical approach, with the exception that it seeks to enable the remarkable, as stipulated in the objectives of the competition. But as you've seen, there have been a number of new approaches that have been developed in recent years. What's important here is that the learnings from different domains can provide insight and solutions to technical challenges for other applications. Historically, the trends in VTOL technologies have been driven primarily by the desire to hover efficiently and fly fast. Doing them both together, of course, has been a big challenge. There have been some successes in hybrid or compound systems, the tilt rotor, the lift offset compound being two examples of aircraft capable of extended hover while flying fast. But morphologically, helicopters look the way they do for a reason. But this is no longer the case in terms of power and propulsion integration. And today, numerous new concepts have been developed and proposed to enable vertical flight and personal air vehicles, all being enabled by the ubiquitous availability of materials, new systems, new design methods, affordable components and skills, and all of these woven together by the fabric of modern communications and information sharing. This is a particularly exciting time in the development of vertical flight. Indeed, recent trends in man-rated VTOL aircraft, typically involving some level of electric, hybrid, or mixed propulsion, have shown exponential increases in the number of aircraft projects during the past decade. In fact, by current count, well over 130 concepts are at some stage of development, and this discounts unmanned and other smaller UAS systems. So with this in mind, let's take a quick look at the effort and what needs to be accomplished. In February, the competition is looking for solid proof of viability, with phase 2 awards being announced in March. Thereafter, it's a mad dash to integration, testing, verification, and preparation for flight test, executing pre-competitive flight test, addressing requirements, gathering data in support of flight readiness, and then finally followed by a competitive fly-off in September, or rather in October. Accomplishing all of this within 3/4 of a year is going to require some carefully orchestrated efforts to address everything from personnel and inventory management, fabrication, subsystem integration and testing, air vehicle integration and testing, through dynamic simulation, modeling, ground testing, and finally flight. These are activities that are perhaps well underway, but it would help you to track your progress and identify your key milestones and the interplay between subsystems. One of the most important opportunities for you is to ensure you communicate regularly and clearly between team members. Don't just schedule formal periodic meetings, maintain clear and open channels of communication, and push information to each other. Make sure the people who know you, or rather the people who need to know of changes, are informed directly and not through indirect means. So where I was pointing out that we need to recognize that while time is of essence, you will see more time and effort by pausing to measure twice before cutting in executing your program. Some rework and respins are inevitable, but if you can devise clever trial or proof of concept approaches to improve your execution of difficult technical areas, it is highly recommended that you do so. Recognize, identify, and address the systems that will likely pose challenges, and prepare yourself for surprises. Those easy technical problems you neglect or put off till later, in all likelihood, will come back and bite you. Recognize and acknowledge the time required for software development. Verification and integration will take much longer than you anticipated. You might be surprised at how much time and effort this could require. The important takeaway here is anticipate and speak to your peers to learn from them. It will also help you stay on track. There is a lot of knowledge out there. You don't have to reinvent everything. Include the involvement of outside experts or cross-functional groups to help identify lapses and oversights before they become misses that require intensive corrective actions. In preparing for flight tests, there are a few things in life that will keep you up at night, like anticipating the arrival of a baby or preparing to launch your aircraft and replaying everything you've ever done and second-guessing yourself before first flight. My suggestion here is to prepare carefully and deliberately. When our first baby was due, we attended classes on what to expect. We went to every class except the one on delivery by cesarean section because it wasn't relevant to us. Well, guess what happened? You will have a lot of items to keep track of and to keep straight. Even for seasoned developers, first flight and flight test in general is an intense process. Plan your activities carefully, know your players, understand their requirements and how you will address them, plan for contingencies, big and small. Flight readiness and safety of flight board reviews often look for quantitative data to assess preparations for flight. Start capturing data early on, including during your bench testing. And subsystem verification testing can also provide a lot of significant and important information. Often, information gathered during early testing periods can help substantiate and corroborate data required for flight. And you can adopt systems and methods to minimize overhead burden so that you're not having to document everything formally, but can do it in a streamlined manner. Remember, we don't build an airplane to break them. Develop acute self-awareness early on, know your system strengths and weaknesses, design for them, and you'll sleep a lot better after your flight test efforts. This chart simply offers an example of how you might want to portray your data for analysis and review. I often found it most useful to create big picture or holistic perspectives that are based on traceable data and information that include validation efforts. For example, your solid lines may be predictions and the gray lines may be data that you acquire during your validation period. The chart shown here also shows time traces of aircraft state. You can include power polars, aircraft attitudes, energy consumptions, other things that are relevant, including transition corridors. There are many ways to do this, but showcasing your data will help you understand your aircraft and its systems, as well as increase the confidence of your evaluators, especially as you're preparing for flight test. This will be relevant for readiness and to grant you your clearances. In the same vein, it would behoove you to distill your subsystems into systematic domains to help identify key elements of the technical program that must be addressed. These include sharing information across subsystem groups, supporting the development of system interfaces, looking for potential failure points and their impact, all of which will support your ultimate success. It is very important to retain some margin in critical systems, be it performance margin, redundancy, or alternative backups. Should the need ever rise to pull on one of them, you'll have a successful fly-off. Anticipating is important here. Try to position yourself into an operational scenario and look back to see what you may have wanted to adjust while you're executing. System hazards. There are documented processes to capture system hazards and to identify them. I don't know to what extent or level of detail you'll have to assess the probabilities and consequences of potential failures, but you should attempt to identify them for yourselves to avoid derailments. You may not be able to mitigate all your risks, but if you have a plan, maintaining awareness will help you avoid them, or at least they won't catch you by surprise and you'll know what to do to minimize their severity. Indeed, you may have to reconcile to accepting some highly unlikely but high consequent risks. Maintain transparency on your reasoning and it'll serve you well. This chart shows how, for each hazard associated with any subsystem, the consequences of the hazard, and the likelihood of realizing it combine to assign a risk code to it. These are standard practices. And when developing a hazard matrix, don't just think of or consider the highest risk hazards, rather be sure to capture your low risk hazards as well and justify why they are not of consequence. Being systematic will help avoid misses and avoid unanticipated events and demonstrate holistic yet detailed awareness of your flight readiness to your flight readiness assessors. And in parting, I offer that you accept my comments as guidelines for your consideration. These are based on my observations and experiences. They're offered to share experiential knowledge to facilitate your success. Your participation in GoFly will result in much more than a fun, incentivized fly-off. You will develop and hone new ideas, create new opportunities, and discover applications that have not been considered before. Most of all, enjoy the journey. And thank you for your attention. Good luck, and go fly high. Thank you.
Thanks, Ashish. We have several questions coming in. If we can take some time to address them.
Yes, I think we have plenty.
The first is regarding, at some point you had mentioned that you designed an electric rotorcraft controlled by variable CG. And so the question is, how is the CG varied? And I can offer some context from the participant if that would be helpful.
Sure, if you can.
So they have said that many years ago, I designed an aircraft with pneumatic tubular booms included in the wings and tail, along which a mast could be driven at high speed to replace movable surfaces. Plus, of course, large airliners shift fuel around to optimize the pitch trim in the cruise. Along with human weight shift, I cannot think of any other means besides these three. So he's intrigued to hear how you are varied the CG.
Indeed. So here the novelty of the design is less in the novelty of what you're moving. We, in essence, are also moving fuel, if you will, for our energy system. The motivation here was to design and build a scaled X2 type aircraft, all electric. And when I say scaled, it means lab scale at a university level. So it's about 20 pounds or so. And the idea here is to capitalize on the battery mass that's carried on the aircraft and use that for variable CG, and use that to control longitudinal and lateral controllability of the aircraft. The idea was to remove all the swash plate and rotor control systems from the rotating frame that is typically installed in rotorcraft or helicopters, including the X2 type lift offset devices, to use variable RPM because it's an all electric aircraft for thrust control or the equivalent of collective, but then to use the positioning of the battery mass, which in other applications would have just been dead mass on board, on a rack and pinion system, and move it both longitudinally and laterally. So it's not different from moving a mass on board. It's more a question of economizing on adding additional masses. And in this case, since it's an electric system, it's a battery, the fuel package is the battery. So we're looking at moving the battery within the fuselage to provide lateral and longitudinal control.
Okay, great. And more broadly, I think you've addressed this a little bit, but if you can speak to some of the hardest things about making revolutionary new technology.
Well, one of the hardest things is psychological, perhaps. It's the ability to crawl out of your thought paradigm and to step outside your comfort zone. It's sometimes challenging to set aside what you believe you've been taught and what you know to address elements that are not necessarily obvious. One of my reasons for constantly bringing up during my presentation the importance of bringing outside peers or cross-functional group oversight into a picture. It's also not a bad idea sometimes to bring people in who have absolutely no background in this domain. It's not that they will come up with violations to physics. The engineers on the program are the ones who have to take care of that. But there are often constraints that we impose on ourselves. So getting that right is important. with respect to some of the more, in a more technical format, some of the more challenging elements to the design of these aggregate systems is that we have very little in way of design guidance. We don't have any rigorous or parametric descriptions of rules of thumb for conceptual design, for example. So both driven by competitiveness, but also by the lack of information or ubiquitous information relevant to this new design paradigm that's enabled by disaggregate systems or distributed propulsion, is the lack of information. So we have a lot of people who are relearning things, or perhaps not relearning, but learning things by doing. And that's a challenge, because I think what often happens is that to deconflict between different configurations, people come up with novel ideas only to discover that stability and control is much more of a problem than perhaps it should have been, or had it been anticipated correctly. So I think these are a couple of areas that are challenges.
And do you have any tips on dynamic scaling?
Well, dynamic scaling is a tough one. Look, I don't know whether I have tips on how to go ahead and dynamic scale, other than pointing out that you can probably apply scaling laws within certain groupings of aircraft. If you go from very small handheld or a few pounds or a few tens of pounds to something that's hundreds of pounds, you're probably pushing the limit. So it's necessary to operate or develop systems that are in the correct operational space. It's a great question, and it's one that I think is a challenge faced by everyone. There are other elements that one can bring to bear when it comes to dynamic scaling. I'm not sure whether the person is asking about dynamic scaling from an aeromechanics perspective, a dynamics perspective, vibratory loads, or resonances. I can give you an example of something novel that we did recently at the University of Maryland regarding the amorphous two-dimensional flying structure. We wanted to make this a very flexible structure, but of course, when you make it flexible, you end up with resonances because at low frequencies during startup or low RPMs, because you excite different modes. So one thing that I had my students do was to start using embedded materials or sandwiching materials within substrates of construction material that would serve as structural dampers. So, even if you don't necessarily understand all your scaling and you don't necessarily have a good way to take something that's at small scale and apply it directly to large scale, you can sometimes apply techniques that can help resolve them. I think this is a little bit of a mix, and it's not that I advocate just doing things without understanding them, but I do advocate looking for new solution spaces to address the problems. I don't think you have to analyze them and solve them in the traditional sense every single time. So I would offer that for consideration.
Great. And what has been your process like, or your suggestions on how our innovators might approach the process with the FAA?
So the guidelines that I provided are less focused on either the military or the FAA. I think my general comments, and this is why I touched so heavily on flight tests and had maybe 2 or 3 charts on that, was that the more awareness, look, you're going to go for an experimental. This is not a production or a type certificate that you're going after, but you're going to go after a flight clearance. And it's very important that the most important thing you anticipate or exhibit is safety. And I think GoFly makes that very clear. But second to that, it should be safety based on awareness and cognizance. I think it's very important that you approach your functionality and your system functionality, both at the subsystem level and at the integrated system level, in a manner that is extremely deliberate and expresses a very high level of self-awareness in terms of what you've done, why you've done it, and why you're making a recommendation. With that in mind, I think any assessor who sees that would be much more comfortable understanding and granting you your clearances when it comes to your flight clearances. And I saw that happen on some of the programs that I executed before, where maintaining transparency and not just highlighting the things that work, but underscoring the weaknesses and why those weaknesses were acceptable without fixes, was concerned I think leads to a lot of confidence. So again, my approach would be in a general sense. I would recommend being transparent, being clear about what you know, and spending a lot of time knowing your system really well so you can really speak to it.
And so you spoke about obviously safety, and that's certainly a big part of the GoFly program. Can you talk a little bit more about the things that innovators should be looking for, the team should be paying attention to when it comes to safety, and how they should be ensuring safety in their devices?
Okay, so at a holistic level, the chart that I showed that has that's titled Know Your Systems, which has the fan diagram of different domains branching out into different systems. The intent of doing that is to actually help do exactly what you pointed out, is to try to be aware of what your systems are, understand how they interplay. But the first thing you have to do is to list them out in a distilled, systematic, sensible manner that makes sense. Because from that, it's almost a fall tree. It's not really a fall tree, but it is a tree. Is that it helps you identify those areas that you know with confidence, and it helps you identify those areas that you perhaps don't understand as well, and you may need to come back and spend more time addressing. So from the perspective of addressing safety, I think the most important thing is to make sure that we don't end up with a system that is going to result in a catastrophic failure. Whether you have a pilot on board or not is relevant, but is not the only criteria that decides on whether something will be a catastrophic event. So I would highly recommend that you look at those elements and you understand what your failure modes are, and then what the consequence of those failure modes are, while fully understanding what the probability of those failure modes are. I also mentioned in my talk right now about gathering data early on, whether it's bench testing or during bench testing or early subsystem development. Look, what happens is that people look to integrate the airplane and then go out and try to gather data. But if an FAA or another flight release authority assessor is looking for a failure or the likelihood of a failure, every test that you've done with an engine or every test that you've done with a retraction with an actuator is actually generating data. And if you can capture that data early on and understand that that can also contribute to a statistical database of how many failures you may have had per actuation that you've done, even though the actuation may have been done on a bench test, it's providing really important information. It's providing data that you can provide to an assessor to consider that you have a level of confidence for a reason.
And how do you mitigate some of these safety risks that you're then sort of talking about?
Well, some of these things have to be done through redesign, if there's just no way around them. Others are done by careful integration, I would say. Others are done through careful operations. There are a variety of different ways of doing these things. I've always been concerned about operating a VTOL aircraft in vertical mode, and we, no matter how many people I've come across who are getting ready to execute flight tests, the question always comes up as to how high off the ground should we get during the first flight. There are advantages of staying not too high above the ground, because you don't have too much potential energy. If you come down with a thump, you probably do some damage. You don't break the airplane. On the other hand, you're operating in an unsteady in-ground effect, which is a highly unsteady aerodynamic environment, which is likely to induce additional considerations. So the question then becomes, how do you want to mitigate that? What's a bigger risk? Are the unknown unknowns bigger than the known evils? And do you err on the side of accepting a known evil? There may not be much of an option sometimes. Maybe you start off by doing some tethered ground, or I don't like tethered, but maybe tie-down testing. And maybe the tie-down testing can give you an idea of how unsteady the environment is during the time of that tie-down testing, to help you understand whether or not you likely have a lot of wake feedback, for example, in ground effect. That may help mitigate some of your risks. So the different approaches, and obviously risks have to be assessed, and mitigation approaches have to be developed based on each system and each hazard that system may pose. If an electric motor burnout is something that could lead to a cascading failure, then you have to decide whether you're really going to put a human being inside the airplane or not, until you can convince yourself that it's not going to lead to a cascading failure, for example. Or as I mentioned in my earlier example, you may run a variety of different tests on these motors to determine that the likelihood of failure is very low, even though the failure may result in bad things happening. So it's ultimately the probability and the consequence of the hazard being realized that matters. And that's how assessors also look at these things. So I would consider doing it on a system by system basis. And it does require work. It does require careful thought. That's kind of why my chart also says give yourselves time to think. Running headlong into something results in oversights.
And I don't have particular context around this question. So Alex, if you'd like to offer something, but the question is, do tilt ducts work?
Just like any other rotor system, tilt ducts also work, and tilt ducts also have their challenges. We've flown tilt ducts before. They have been successfully flown on numerous aircraft. I believe tilt ducts are being incorporated at least on 2 or 3 other airplanes that I'm aware of. In real tilt duct fashion, I can think of 3, right up, I mean, big sized airplanes, capable of carrying people. And I see no reason why they won't work. I do think that they have certain challenges. You can see a rendition on the screen of tilt duct being put to good use. That's of the Ares program that I ran when I was at DARPA. And the office artist drew that for me. But yeah, I mean, the general answer is yes. I'm not sure. Again, I don't understand the context like yourself. I'm not sure what the concern is.
Yeah. So Alex, if you'd like to offer us some more context on that, perhaps Ashish can address that a little bit more effectively for you. The next question is, are there any particularly tricky parts about propulsion that our team should be keeping in mind and considering while developing their devices?
Yeah, that's a great question. Perhaps I should have touched on that a little bit in greater detail. I'm not sure whether this means what type of propulsion, or whether it means the collection of a number of smaller propellers or thrusters in aggregate working together to work. In the same context that we have very little in terms of formal guidelines on positioning and arrangement of these propellers, you'll see that there are that some considerations that are really important depend on interactional effects. And these are not necessarily that well understood right now. Interactional effects are important. The induced rotor flow field is important. Whether rotors interact with each other or they interact with wings. NASA developed a couple of different techniques of trying to create useful interactions. Those are really worth considering, right? You probably want to make something work to your benefit in terms of improving your performance rather than taking a drag impact or a vertical load impact just because you happen to put something over a wing. But you have to actually ask a more fundamental question, and that is, electric distributed propulsion systems, and I think many of our concepts that we're seeing evolving these days are based on those, even though not all of GoFly's technologies or competitors may be working on those. But you have to think about it from the perspective of what does increasing the number of rotors really do for you? And if it, helicopters, like I said, look the way they do for a reason. So if you're trying to replace something with a different technology that results in, one must fundamentally ask, what are we trying to do? It enables new configurations, yes, but so what? And how does that matter? But I think the answer is pretty obvious, right? I mean, I don't think we have activity of people going out and trying to make helicopters the way we do people trying to make distributed electric aircraft. So I think to articulate or to justify that is kind of important.
And finally, obviously you've spent the last 30 minutes or so offering advice and tips and information to our teams. Any final advice that you'd like to, that you can share with our GoFly teams as they head into their phase 2 submission deadline?
Nothing that I've already said, I don't think. I think this is much bigger than just GoFly. I think incentivizing it is a wonderful thing to do. It really pulls a lot of people into it. I think if your participants really understand what they're doing in a broader sense, even though the excitement and the accolades that come with winning a prize may not necessarily be there. I think this is remarkable to do at this point in time. So I think, again, underscoring the fact that you have to enjoy the journey, and enjoy doesn't just mean have fun doing it. I mean, of course you're having fun doing it. Nobody does aerospace just for unless it's fun, unless they're really passionate about it. But I think there's a lot more to it than just pursuing a prize. And I think if people can understand that, which I think most people do, it'll be remarkable. I just sometimes feel that it's easy for people to say that the winner takes all. I'm not sure that the winner takes all in this case. I think there's a lot of very powerful takeaway that'll occur because of this.
Great. Thank you so much for your time. I'll give a moment to Gwen to wrap us up.
Sure.
Ashish, thank you very, very much for your advice and your expertise. I think it will be greatly applicable to our GoFly teams. And I echo your sentiments that the GoFly competition is bigger than GoFly, and we hope to truly catalyze the creation of personal flying devices and change the face of mobility, and also support our teams as they create a new future. So thank you for your time today in helping our teams. And to all of our GoFly teams, we are here to help you in any way, shape, or form. Do not hesitate to reach out to us if we can support you. And we wish you all the best of luck, and many, many thanks, Ashish.
Of course, Gwen, my pleasure. Thank you so much. I know we've been talking for a long time.
Yes, we have.
Thanks, Nidhi.
Thank you. Take care.
Thanks, teams. Bye. Bye.